We're now going to learn how to solve exponential and logarithmic equations. So these are equations that we have not explored before, but we're going to use those properties that we've just learned about logarithms to solve these equations. So we will cover exponential equations, logarithmic equations, and then explore a couple of applications of these types of equations. So an exponential equation is an equation that contains a variable in the exponent, something like 2 to the x equals 5. There are three types of exponential equations that we will solve. Type 1 are equations where we can use a one-to-one property of exponential functions. Type 2 is when we need to use the one-to-one property of logarithms and the power property of logarithms. And then type 3, we will use quadratic methods. So in type 1, let's recall first that a one-to-one function means that if f of a equals f of b, then a equals b. Do you remember that? That every x value had to go to a different y value for a function to be one-to-one. So this means that if two y values are the same, the only way that can happen is if the inputs are the same. So we know that the function f of x equals b to the x, that basic exponential function that is either increasing or decreasing based on the value of b. But in either case, it is a one-to-one function because it passes the horizontal line test. So the one-to-one property of exponential functions states this: for b greater than 0 and b not equal to 1, if b to the m equals b to the n, then m must equal n. So this property tells us that if two exponential expressions with the same base are equal, then the only way that can happen is if their exponents are the same. And so to use this, that's what we're going to try to do. See if we can write each side with the same base. If we can, then we'll set the exponents equal to solve the equation. So we have some examples, and the first one is 5 to the 2x minus 9 equals 125. The left side is written with a base of 5, so we want to try to write 125 with a base of 5. And we know that 125 is 5 cubed. So now that we have the bases equal, this means that the only way that can happen is if 2x minus 9 is equal to 3, right? If their exponents are the same. Then we can add 9 to each side to get 2x equals 12 and divide by 2 to get x is equal to 6. We can plug in if you want. We plug in 6 for the exponent. 2 times 6 is 12, minus 9 is 3, so we get 5 cubed, which does equal 125. So our solution set consists of the number 6. B is 8 to the x plus 3 equals 16 to the x minus 1. So these don't have the same base initially, but you're trying to think, can I rewrite 8 and 16 with a common base? And I can if I think about that, right? 8 is the same thing as 2 cubed, so we have 2 cubed to the x plus 3, and 16 is the same thing as 2 to the 4. So we have 2 to the 4 raised to the x minus 1. And now we can apply the power property of exponents that states when we raise an exponential expression to another exponent, we have to multiply the exponents. So on the left, we multiply the exponents of 3 and x plus 3 to get 3x plus 9. And that is equal to, on the right, 2 to the 4 times x minus 1 is 4x minus 4. Now, the left and right side have the same base of 2. We can set the exponents 3x plus 9 equal 4x minus 4. Now we just solved this linear equation for x. We can subtract 3x from each side. to get 9 equals x minus 4. And then we can add 4 to each side to get 13 is equal to x. And then you can, of course, plug in and check that you would get a true statement. So our solution set consists of 13. Part C is the quantity 1/4 to the 2x equals 64 to the x plus 3. So we need to figure out, is there a common base between 1/4 and 64? Well, 1/4 is 4 to the negative 1, so I'll put that in parentheses, raised to the 2x. 64, if you recall, is 4 cubed. I'll put that in parentheses to the x plus 3. So now we have a common base of 4. We can simplify by applying the power rule of exponents. So we get 4 to the negative 1 times 2x is negative 2x, equals 4 to the 3 times x plus 3, which is 3x plus 9. Now we can set the exponents negative 2x equal to 3x plus 9. If we subtract 3x from each side, we get negative 5x equals 9. And then we can divide by negative 5 to get negative 9/5. So our solution set consists of negative 9/5. Now type 2 exponential equations are equations that cannot be written with a common base, something like 2 to the x equals 30. Well, we cannot easily express 30 as a power of 2. So to solve this equation, we will take the logarithm of each side. And so recall that a logarithmic function is 1 to 1, which means that if two expressions are equal, m equals n, then the log of m is equal to the log of n. And once we do that, then we're going to apply the power property of logarithms, which is that log to the base b of x to the r is equal to r times the log to the base b of x. So our whole goal is to try to bring the exponent down, because right, that's where our variable is, bring that down so we can solve for that unknown. If we just look at this basic example of 2 to the x equals 30, right, if I take the log of each side, I would get log of 2 to the x equals log of 30, and this is a common log. So by the power property, I get the x times log of 2 equals log 30. And then I can divide each side by the log of 2. And so log of 30 divided by log of 2 is approximately 4.91. So we will apply those steps. Now, I will tell you this, if your exponential equation involves a base e, then you'll want to use a natural log, because remember that the natural log of e to the x is just x, since those are inverse functions. So in example A, I have e to the x equals 7, so I'm going to take the natural log of each side to get the natural log of e to the x equals the natural log of 7. Natural log of e to the x is just x, but for some reason, if you didn't remember that, you can write that as x times the natural log of e equals the natural log of 7. But remember that the natural log of e means what is the exponent of e that gives us e, and that is just 1. So natural log of e is just 1, so x times 1 is x equals the natural log of 7. Now, you could use your calculator to approximate that value, and it would be approximately 1.95. But the exact answer is the natural log of 7. So in our solution set, we'll have the natural log of 7. Part B is 4 to the x equals negative 9. And so if we used the common log to take the log of 4 to the x equals the log of negative 9. We would get x times the log of 4 equals the log of negative 9. But do you remember this, that the argument of a log must be strictly greater than 0. And so the log of negative 9 is actually undefined. So let's say you didn't remember that and you divided each side by log of 4. But if you enter this expression on your calculator, that is a log of -9 divided by the log of 4, you're going to get an error. Right? This is undefined because the argument must be greater than 0. How could I observe that at the beginning? Recall that 4 to the x, right, the exponential function, always has an output that has to be positive, right? It goes to that horizontal asymptote of y equals 0. So 4 to the x can never equal some negative number. So this one has no solution, which we denote as the empty set. Part C is 6,000 equals 3,000 times e to the 0.05t. To take the log of each side, we need to isolate the exponential expression. So we first need to divide each side by 3,000, since that is a coefficient of the right-hand side. And then we get 2 equals e to the 0.05t. Now, because our base is an e, we'll take the natural log of each side. So this tells us a natural log of 2 is equal to the natural log of e to the 0.05t. We get the natural log of 2 is equal to 0.05t. Remember, the inverse property is the natural log of e to the exponent, whatever it is, it's just going to be the exponent. So to solve for t, we can divide by 0.05. So when we approximate that value, it is approximately 13.86. But again, our exact answer would be the natural log of 2 divided by 0.05. D is 5 times 1.2 to the x plus 5, then plus 7 equals 12. So in this problem, we need to get this 1.2 to the x plus 5 on this side by itself before we can involve logs. So we would first want to subtract 7 from each side to get 5 times 1.2 to the x plus 5 is equal to 5. And then we can divide each side by 5, which gives us 1.2 to the x plus 5 is equal to 1. Now we have the exponential expression isolated, so we can take the common log of each side to get the log of 1.2 to the x plus 5 is equal to the log of 1. On the left, the power property of logs tells us this would be x plus 5 times the log of 1.2 is equal to, well, the log of 1 is actually 0, right? Because 10 to the 0 equals 1. And so I can rewrite this as x times the log of 1.2 plus 5 times the log of 1.2 is equal to 0. So to solve for x, I can subtract the 5 of log 1.2, so I get x times the log of 1.2 is equal to -5 times the log of 1.2. And then we can divide each side by the log of 1.2. So when we do that, we get x is equal to -5. And actually, in this step where I had x plus 5 times the log of 1.2 equals 0, I could have divided each side by the log of 1.2 there. To just get x plus 5 equals 0, or x is -5. So either way is acceptable. And then one last example for this type. If we have 4 to the x plus 1 equals 3 to the 5x minus 2. So here again, we have an exponential equation with a base that cannot be written with a common base. Each exponential expression is isolated. So we will start this problem by taking the log of each side. So we have the log of 4 to the x plus 1. Now again, I could use a natural log if I prefer. It's equal to the log of 3 to the 5x minus 2. So we can bring the exponent down by the power property to get x plus 1 times log of 4 is equal to 5x minus 2 times the log of 3. Now our goal is eventually to try to get x on a side by itself. So we need to multiply each side out to get x times log 4 plus 1 times log 4, or just log 4, is equal to 5x times log 3 minus 2 log 3. So now we need to get all of the terms with x on one side and everything else on the other. So I'm going to subtract the 5x log 3 to get x log 4 minus 5x log 3 is equal to, and then I'm going to subtract the log 4 to get negative 2 log 3 minus log 4. So far so good. I know this one's pretty complicated, but now I want to notice that I have x on the left in two terms, so to get x by itself I need to factor the x out of those two terms. So this would give me x times log 4 minus 5 log 3. And that's equal to negative 2 log 3 minus log 4. Now to solve for x, I'm going to divide by this ugly coefficient, but it is the log of 4 minus 5 log 3. And in doing that, I get what x is equal to. X is this quantity, negative 2 log 3 minus log 4, all divided by log 4 minus 5 log 3. And so you could enter this on the calculator to find the decimal approximation. To do that, I would need to put the numerator and denominator in parentheses. And notice that the arguments of all of the logs also need to be in parentheses. And so whenever you compute that, you're going to get that this is approximately 0.87. But the exact answer in my solution set would be this negative 2 log 3 minus log 4, all divided by log 4 minus 5 log 3. Now the last type of exponential equation we'll solve is ones that are quadratic in form, and we can use quadratic methods to solve these equations. So we're going to see something like this. E to the 2x plus 2e to the x minus 15 equals 0. So notice that this linear term, really e to the x and e to the 2x, are related in the fact that if we square e to the x, we actually get e to the 2x. And so if we let u equal e to the x, we would actually get this when we make the substitution. E to the 2x is u squared plus 2u minus 15 is equal to 0. And now we can solve this by factoring. The factors of 15, whose difference is 2, are 5 and 3. And we need a plus 5 and a minus 3. So we get that u plus 5 is equal to 0, or u minus 3 is equal to 0, which gives us u is equal to negative 5, or u is equal to 3. But remember, we're not solving for u, we're solving for x, so we would rewrite this as e to the x equals negative 5, or e to the x equals 3. Well, e to the x equals negative 5 is a contradiction because e to the x is never a negative number, so that will not give us a solution. To solve e to the x equals 3, we can take the natural log of each side. To get the natural log of e to the x equals the natural log of 3, So x is the natural log of 3. Now again, you could approximate that on your calculator if you wanted to, but the precise answer is the natural log of 3. And here's one more. We have e to the 2x minus 3e to the x plus 2 equals 0. If you don't want to use u substitution, you could just factor it initially, just remembering that the factors of e to the 2x are e to the x and e to the x, right? Because e to the x times e to the x, like bases, we add the exponents, x plus x is 2x. And then the factors of 2, whose sum is 3, would be 2 and 1. And we know they have to be the same sign, and they have to both be negative. So we have e to the x minus 2 times e to the x minus 1 equals 0. We can set those factors equal to 0 to get e to the x minus 2 equals 0, or e to the x minus 1 is equal to 0. We add 2 to get e to the x equals 2. And then we can solve that equation by taking the natural log of each side. So the natural log of e to the x equals the natural log of 2. This gives us then just x equals the natural log of 2. Solving the other equation, e to the x minus 1 equals 0, we can add 1 to get e to the x equals 1. And then when we take the natural log of each side, we get the natural log of e to the x equals the natural log of 1, which is just x equals 0, right? Because e to the 0 is 1, so the natural log of 1 is 0. Therefore, our solution set consists of 0 and the natural log of 2.